Hello, folks, and welcome back for part two of series and parallel circuits. This time looking at solving multi-loop circuits with Kirchhoff's laws. So you know you can't use the simple series and parallel equations when you have a circuit that looks kind of like this, one which has like multiple batteries in it and resistors both in series and parallel. And so you're going to want to use the laws to help you solve these ones. These are not the easiest, but by setting up some equations, you can actually make it a little bit better. Now, one thing I'm going to do right away is I know I can make this a little easier myself. If I were to eliminate these two resistors and replace them with an R5 being 7 ohms. I know I can do that because those are in series. But now I got a weird thing. I can't just say these two resistors are in parallel, R5 and R7, if I put R5 here, let's say, because there's this battery in the way here. And so I end up getting a situation where I need to use Kirchhoff's laws. Now, what I'm going to do is use all of them. I am going to use first the loop laws. I'm going to assume that the current is going to flow this way through this loop. You have to make this assumption, and you might be wrong. You might end up getting a current that's negative, and that's okay. It just means your loop was the wrong direction. But you do have to make sure you make that assumption. I'm just going from positive to negative there. Now, in that loop, then, remember, voltages across batteries will add if you're going the right way. So I get V1, and then I know that it's going to go down across a resistor. So minus I1 times R1 minus I2 times R2 has to equal 0, where I1 and I2 are the currents through R1 and R2. They might not be the same because the current is going to split there. And in fact, I could say that at that junction, I1 plus I5, the current going this way through this resistor, is equal to I2, the current going out that way. So there's I2, I1, and I5. So those have to be equal. And then lastly, my last loop, I would say that V2 minus, that should be an I1 there, minus I5 times R5 minus I2 R2 has to equal 0. Now I could do the current junction here, but it actually ends up not mattering because it's the same equation essentially that I get up there. And so I'm not going to need that equation. Now, there's a few different ways you can solve these types of problems. One thing I might notice already is that my two equations here are sort of similar. I can first off replace I2 in both of them with I1 and I5 to get two more simple equations. So I'm going to go ahead and do that. So I'm going to say that V1 minus I1R1, and then replacing I2 with I1 I5, I get minus I1 R2 minus I5 R2 equals 0. And then for the next one, V2 minus I5 R5 minus I1 R2 minus I5 R2 equals 0. Now, one thing that's nice about this here is that I can see that there's a term that is the same there's some terms that are the same in both of these. And I could have just done this up here, but I wanted to kind of get my equations a little bit simpler, just in I1, in terms of I1 and I5. And so what I'm now going to do is I'm now going to take this top equation and subtract off the bottom equation, because that's one way I can solve a system of equations that have two variables. Remember, I know what V1, R1, R2 are. So it's not like I'm not, these are actual numbers. So the only numbers I don't know are I1 and I5. I'm not going to put any numbers in yet, just to kind of help simplify the math here a little bit. So I get V1 minus I1 times R1. And then notice that these two, I get minus I1 times R2 minus a minus I1 times R2. Those will cancel and those will cancel. And so I'm just left with minus V2 and then plus I5 times R5. And that has to equal 0. I'm now going to go ahead and solve my equation to get I5 in terms of I1 or vice versa. So V1 is 24 volts. minus R1 times I1, so 3I1 minus 29 volts there. And then finally plus R5, which was 7 ohms, times I5. That has to equal 0. So 24 minus 29 is minus 5. And then I get that minus 3I E plus 7 I5. That's an I1, by the way, equals 0. And so solving this out, I end up getting, it looks like, that I1 equals 7I5 minus 5 divided by 3. Not the most clean equation, but I now have I1 in terms of I5. I then can plug that all the way back up into one of these equations. Let's go ahead and do it. Looks like I did it into the V1 equation. So let's go ahead and do that. So V1 is 24 volts. Then it's minus R1 times I1. So minus I1, which is all of this, 7I5 minus 5 divided by 3 times R1, which is 3. Then minus I1 again, 7I5 minus 5 over 3 times R1, which is 3. And then lastly, minus I5 times R2, which again is 3 ohms. Okay, so solving that out, and that has to all equal 0, by the way. So 24. And then notice the 3's will cancel here. And I get minus 7I5 minus 5 times 2. There's 2 of them. So I'm just going to kind of loop those in there, be minus 14I5 minus a minus 5 minus another minus 5. So plus 10 minus 3 more I5s equals 0. And so solving that out, I get 34 equals 17I5. And so I5 equals 2 amps. This is the point where you feel very happy because you're like, okay, I'm getting some easy answers now. This does make sense. It's a lot of math and equations, but you can eventually get there. Once you get that, you can plug in here. I1 would be 14 minus 5 over 3. 14 minus 5, it looks like, is 9, right? And 9 divided by 3 is 3 amps. And so perfect. I know I1 is 3 amps. I know I5 is 2 amps. If I wanted to, I could easily figure out what I2 would be. I2 would be the 3 amps plus the 2 amps, which would be 5 amps. And then I could solve for anything I wanted in this circuit at this point. But I don't want to because that's a lot of work. And I've already done a lot of work. Once you get those final currents there, you're pretty much in the clear there. So that's how you solve a multi-loop circuit using Kirchhoff's laws. Okay, the last thing we got to do tonight is throw some capacitors in the mix here. Now, capacitors in circuits, we're not going to look too much deeper than just looking at what are called RC circuits, circuits that involve a resistor and a capacitor. Essentially, there are 2 versions of this. You can either charge a capacitor or discharge it. You charge a capacitor when you have the battery here. Go ahead and line up with your capacitor such that the capacitor is being charged up by the battery. The battery's voltage is charging your capacitor. And what happens is that if you have this as your voltage of your battery and this is time, your capacitor will asymptotically approach that voltage so that the voltage of the capacitor is that voltage that's at your battery there. And so we can define the amount of time it takes using these equations here, where Q here is the charge that's currently on the capacitor. It's equal to the capacitance times voltage of the battery times this mess. That, by the way, is not the elementary charge, but it is E, the natural log, or the base of the natural logarithm, and then minus TRC. You can also define the current through the capacitor, or of course the voltage of the capacitor at different time points there. One thing to note is this tau thing here. It's called the time constant, and that is that denominator on the bottom. The time constant kind of represents the time it takes to reach a certain point of charging. That point is actually 63% of being fully charged up. To discharge a capacitor, you would disconnect it from the battery, like using a switch here, and move it to B. If it was on B, then the charge would be flowing this way, and your capacitor would kind of act like a battery until, of course, all the charges, the electrons, would flow back through there. And so it's going to discharge. The current, or the charge is going to go down with time. Same thing with the current, and then same thing with the voltage of the capacitor. Let's try a few examples of how these equations would work. It's given me here an example circuit, and it's asking me what is the time constant for this particular capacitor resistor arrangement. Well, the time constant, tau, is just the resistor times the capacitance. It tells me that the resistance of the resistor is 47,000 ohms, 47 kilo ohms. So 47 times 10 to the third ohms times the capacitance, which is 1,000, times 10 to the negative 6, because it's microfarads. And if you solve that out in your calculator, you actually get a convenient number, 47. Now, the unit of the time constant is ohm farads, which conveniently is actually seconds, which is nice. So an ohm times a farad is a second, which is convenient because that's why it's a time constant. That's telling you that this circuit has a time constant of 47 seconds. After 47 seconds, the capacitor will be about 63% charged. And so you can use that as a way to kind of measure how long it's going to take for this capacitor to charge up. And remember, we had said capacitors are super useful in a lot of electronics. And so when they're designing electronics, they pick resistors and capacitors such that the time constant makes sense for whatever you are using it for in your circuit. Now it says, what's the voltage across the capacitor after 30 seconds? Here, I'm going to simply choose the equation that makes best sense. And here, I'm actually doing a charging circuit, right? Because the battery is connected, and that would flow through here. And so I'm going to pick a charging equation for the VC. VC is equal to the voltage across the battery times 1 minus e to the minus t over RC. Plugging in my numbers, the voltage across the battery is 5 volts times 1 minus e minus the time is 30 seconds divided by RC, which is my time constant, 47. And so solving this out, remember, don't take the exponent or the exponential function to the negative 30 over 47. And when I do that, I get 2.4 volts, which makes sense. We're not quite very far in my circuit. It's only been 30 seconds. The time constant's 47, so my capacitor is still charging up. But if you let time just keep going up and up and up, eventually it will reach 5 volts there. Okay, folks, that's been a lot about circuits, some quite complicated stuff, as well as some easy stuff with series and parallel. Thank you guys so much for watching. Have a great rest of your day.